So in the previous segment, we wrote the Hamiltonian operator in terms of another operator, which we denoted by n. And we showed that the Hamiltonian and this new operator commute with each other. And we made the statement that any eigenstate or any eigenfunction of the Hamiltonian will also be an eigenfunction of this new n operator. So this is just dependent on the fact that they commute. It has nothing to do with their structure, their explicit relationship. So this is kind of a theorem, and let me prove this. So the theorem is that suppose A and B are two operators which commute. So this means A commutes with B. So then let psi be an eigenfunction of A, meaning that A acting on psi give me some number small a times psi. Then the theorem states that psi is also an eigenfunction of B. So then this implies that if B acts on psi, then psi is also an eigenfunction for some number B. So here we are assuming that psi is a what we're assuming is that A is a non-degenerate eigenvalue of A. What does this mean? This means that if A is an eigenvalue and the eigenfunction corresponding to A is psi, there's only one eigenfunction. There is not more than one eigenfunction. So that is what non-degenerate means. So the proof is very easy. So we start with the fact that psi is an eigenfunction of A, and then we apply B to this equation. So we multiply this equation by B from the left. And because B and A commute, we can write, before we do that step, let's just write this as B times A acting on psi, or B times small a acting on psi. But B and A commute because they are, that's the assumption. So that can be written as A times B acting on psi. And small a is just a number, so of course it will commute with B. So I can write this A times B of psi. And this thing can be written as A times B of psi is equal to A of B of psi. And thus we see that the state B of psi, which we can call, say, psi small b, this is also an eigenstate of A with the eigenvalue small a. But we assume that A is a non-degenerate eigenvalue. That means that there's only one linearly independent eigenfunction corresponding to this eigenvalue. So that means that psi b, which is equal to B times psi, must be proportional to psi. And if I write this proportionality constant as small b, we see that psi is also an eigenfunction of the operator B with the eigenvalue small b. So psi is called a simultaneous eigenfunction of A and B. And of course, we have proved the theorem. So now let's come back to our particular case. In our particular case, H is equal to n plus half times h bar omega. So let's assume that, the eigenfunctions of H are denoted by psi n. And these are given by some energies, which we will call En times psi n. And that then the eigenfunction psi n is also an eigenfunction of n. And that is going to be, let's denote that eigenvalue by small n. So then what this relationship means is that, it means that the value that H acting on psi n will give me small n plus half h bar omega psi of n. So these will be the eigenvalues En. So if I can solve this equation, then I will automatically have solved this equation.